My name is Saritha Mohanty, and today I'll be talking about my thesis titled Identifying Land Use and Meteorological Factors Associated with the Ratio of Personal PM2.5 Exposures versus Ambient Concentration in a Panel of college Students. To give you some background, PM2.5 particles are fine particles with an aerodynamic diameter of less than 2.5 micrometers, and PM2.5 levels in the air are often used as an indicator for overall air quality. Many studies in the past have shown a positive relationship between high levels of PM2.5 and adverse health outcomes. Small, low-cost, portable PM2.5 monitors are especially useful in capturing the spatiotemporal variability in air pollution that results from traffic volume, distance from sources, pollutant chemistry, and local weather patterns. The DRIVE study was conducted to measure traditional single pollutant and novel multi-pollutant traffic indicators along the busiest and most congested highway artery that is also right next to the Georgia Tech campus, as shown in the picture here. In this study, 34 students from the Georgia Tech campus were asked to wear micro-PEM monitors from September to December of 2014. The main aims of this thesis are to develop models for the ratio of personal exposure to PM2.5 versus ambient background levels using predictors such as meteorological conditions, time of day, and distance to major roadways. We focused on ratio PM2.5 rather than the actual personal exposures in order to elucidate factors that can contribute to error associated with use of background levels measured at standard fixed location monitors. There were three main data sources. The first one was personal exposure measured by the micro-PEM monitor every minute. The second was location data measured by the GPS tracker every second. The location of the GPS measurements in the Georgia Tech campus is shown on the left here. The bottom left image just shows one example of one subject's personal PM2.5 measurements as he or she moved on campus between 6 to 7 p.m. on November 10th. The third data source is meteorological and background PM2.5 levels measured by the stationary monitors around campus every hour. The first step was to create rules so that all data sets could be at the same temporal level. Once we had the main analytic data set, we derived some variables such as an indicator for whether the subject was indoors, whether the wind was blowing towards the subject, the time of the day, if a secondary road was within a 50-meter buffer area from the subject and the distance to the main highway. We then fit a linear regression model by first fitting a full model with all the predictors. We used a regression subset procedure to select the model with the maximum adjusted R-square value. This model is shown on the PowerPoint. We then fit a random forest regression model with a split rule based on minimizing variance. We use the same predictors that were in the reduced linear regression model. The importance of each variable in the model was based on the variance of the response variable. And finally, we created a 100 by 100 grid that was overlaid on the Georgia Tech campus as shown here. Each grid cell measured an area of 18 by 18 meters. We used the model to predict ratio PM values for each of the grid centroids. The linear regression model gave us insight into the direction of the predictors in relationship to ratio PM2.5. For example, we see that ratio PM2.5 actually decreases when traffic count increases. This might be because an increase in traffic in the main highway creates a higher level of ambient air pollution and therefore reduces the ratio of personal exposure to ambient PM2.5. The random forest model told us which variables were most important in determining ratio PM2.5. We see from the chart here that the relative humidity appears to be the most important, followed by distance to highway. We also, using the models, we predicted in-sample ratio PM and compared them to the observed ratio PM. The figure here shows that the random forest model is actually better able to capture extreme values and provides estimates that seem to be more similar in distribution to the observed ratio PM2.5. Finally, we predicted values for the 100 by 100 grid for each of the time intervals and got the following maps. We see that the time period between 10 a.m. to 4 p.m. has the highest ratio PM, meaning that the personal exposure appears to be more than the ambient air pollution. Limitations of this study include the relatively small area of the Georgia Tech campus. We also did not consider the GPS error, which can have significant effect on several of our derived variables. We also do not have data into the adherence of the participants in the study and if they carry the personal pack with the monitors throughout the study period as per instructions. The next steps include creating separate models for each of the time intervals and seeing how the important variable list changes. We could also model using personal PM2.5 exposure as the outcome variable. And finally, it is worth investigating why the random forest consistently predicts lower ratio PM levels right adjacent to the highway. That is all. Thank you so much for your attention.